This video shows how to construct Taylor series expansions to approximate complex functions with polynomials. This fundamental calculus technique appears on AP exams and enables advanced engineering calculations. You'll learn to find derivatives at a point, apply the Taylor formula, and determine convergence intervals. We'll build a polynomial that matches a function's value, slope, curvature, and every higher derivative at a single point. We'll derive the formula, then apply it to e to the x at a equals 0. Finally, we'll watch how adding more terms makes the polynomial hug the curve further and further out. Let's work through it on the diagram. What if you could replace any function with a polynomial? Polynomials are easy to compute, just addition and multiplication. Taylor series make this possible. The formula looks intimidating with factorials and nth derivatives, but the idea is beautifully simple. Match the function's behavior at one point, derivative by derivative. Goal: understand the Taylor series formula, compute it for e to the x, and see why more terms give a better fit. Step 1. We want a polynomial p of x that matches f at a, same value, same first derivative, same second derivative, and so on. Assume p of x is a polynomial centered at a with unknown coefficients c0, c1, c2, and so on. Plugging in x equals a, everything vanishes except c0, so c0 equals f of a. Take the first derivative and plug in a, c1 equals f prime of a. The second derivative gives 2 times c2 equals f double prime of a, so c2 is f double prime of a over 2 factorial. In general, cn equals the nth derivative of f at a divided by n factorial. That's the Taylor coefficient. Now let's apply this to e to the x, the friendliest function for Taylor series. Step 2. Every derivative of e to the x is e to the x, and e to the 0 is 1. Since every derivative of e to the x is e to the x, every derivative at 0 equals 1. So each coefficient cn is simply 1 over n factorial. E to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on forever. The first Taylor polynomial is just 1 plus x, a straight line. Add the x squared term for t2, then x cubed for t3. Let's see how each polynomial hugs the curve a little further. Step 3. As we add more terms, the polynomial approximation gets better over a wider interval. T1 is the tangent line at 0. It matches the value and slope, but curves away quickly. T2 adds a parabolic term. It captures the curvature at 0 and stays closer to e to the x. By degree 5, the polynomial hugs e to the x from about -3 to +3. In the limit, the infinite sum equals e to the x exactly for every real number x. Everything becomes a polynomial. Whenever you need to approximate a complicated function near a point, Taylor series is the tool. Match derivatives one by one. Each new term corrects the next order of error, and the coefficients are always f's nth derivative at a divided by n factorial. For e to the x, every derivative at 0 is 1, giving the cleanest Taylor series of all, x to the n over n factorial, summed from 0 to infinity. That's the power of turning everything into a polynomial.